feedback. Or it's either with when you're group members, or it's up here. You can get it after class. So also hopefully you got back your grades on the first homework. I think you can get comments on there, everything through Canvas. If you haven't gotten alerted that, you can probably figure out how to get that stuff through Canvas. So most of the class did very well. So I'm not going to kind of go over any of the answers because most people got most of the points. So I was pretty happy about that. Just to point out, the next homework, the document hashing stuff is due a week from Wednesday. There's, what is it? Let's see. So if you have questions on that, you should. The first place to look is I updated the assignment just a little bit. There are a few parts where I thought it was a little bit ambiguous, so I tried to make that clear. And there's more discussion on this in the discussion group. If you have further questions, post questions in the discussion group, or you can stop by the TAs. They have the office hours this week and also next week. All right, so and so next week Monday is in our class. All right, so we're going to start the section on clustering today. So let's see. So clustering. So this is maybe one of the topics most associated with data mining when you ask, what is taught in data mining. Often one of the first things might be clustering. Now, no, we're only going to spend 3 lectures on it, so there are lots and lots of types of clustering algorithms. There are literally thousands of research papers just on different types of clustering algorithms. We're going to focus on 3 main types. So there's hierarchical, if I can spell this correctly, archical, and so in particular we're going to look at conglomerates there's assignment-based, and so the most famous example of this is the k-means clustering approach, and then the third one is spectral. Okay, so there are other ways to do clustering other than these 3 basic types. We'll mainly be talking about the hierarchical today, but we'll actually, I don't think there's really that much to say here, so I'll finish this and actually get into the assignment phase. But I won't talk about the k-means yet today. That'll be, all of Wednesday will be on the k-means problem. And then next week, Wednesday, we'll talk about the spectral. And the spectral is where you are thinking of your data as a graph, or you start with spatial data and you convert it into some sort of graph or some sort of affinity matrix, and then you do clustering on that. So this kind of goes through this extra abstract data type of the graphs you can do clustering. So there, there are probably, if you know of these general types, you may think of some clustering algorithm you've seen that, and you think maybe it does not fit in one of these categories. That's quite possibly the case. There's lots of other variations here that we just, so one, you could spend all class just on clustering, but I think that would not really be that useful because there are really 2 types of data when you have that you can consider clustering. There's So if data is clusterable, and I'll define what I mean by cluster shortly, then most algorithms work well. Okay, so when data is not easily clusterable, then most algorithms work poorly. So if your data has well-defined kind of subsets of data, and we'll define this, then it doesn't really matter too much what algorithm you use. There may be some choices in the distance function you have to choose, and that may determine whether your data is clusterable. But most algorithms will work fairly well, and it's not going to matter too much which algorithm you choose. If data is not very clusterable, there is not really these distinct subsets of your data, then it's not going to matter what algorithm you use. Your data is, you're not going to be able to find these different subsets. And so it's, so what the takeaway should be that, clustering is, there have been a lot of people, so there's some gap between these two sets, right? So the data is clusterable, it's not easily clusterable. Maybe there's something in between where it's kind of possible to find a cluster, and there's been a lot of work in trying to kind of go in these types of data which maybe are not obvious what the clusters are, but they should be able to find something. And I'm not sure how much that situation really comes up and how confident you should be about the answer if that's the situation comes up. So we'll go through these three main types anyways. I think they give very different perspectives on how to kind of organize and structure your data. And they kind of give an overview of many of the different flavors. And then, if you're going to run some sort of clustering algorithm, probably in most cases you're not actually going to implement your own algorithm. You'll probably use something out of the box. It'll probably work well. But what you'll need to do is understand the limitations of these different types and how to design and the modeling associated with them. So by going through them, you'll see the different modeling choices involved in all these algorithms. And you'll probably try and run them. And so one of the other questions is what's going to happen is you're going to have some sort of input data. Someone's going to say, well, can you cluster the data? Or you're interested, are there clusters in there? So you run an algorithm. It's going to output a set of clusters. And then what? So how do you know if these clusters are reasonable or not? Well, so that's an interesting question. So maybe I'll try and touch it. That's not an easy thing to answer. So some of these distances between sets, like the Jacquard distance or like the Enberg similarity and Jacquard similarity we talked about, they can kind of be used to say if you rerun an algorithm, how similar are the outputs, how consistent are they? It's very consistent for different types of algorithms. Your data is probably easily clusterable, and it probably doesn't matter which one you use. If you get very different results every time, then your data is probably not easily clusterable. And maybe you shouldn't trust the clusters that much. So in some cases, you'll be able to draw pictures, and you'll be able to see, oh yeah, this clustering really seems to be giving much better answers than other ones, and maybe in some cases some algorithms give the right answer and some don't. And I'll show some examples of the differences between different algorithms. So it's not always that you can draw pictures. You can only draw pictures if your data is really in 2 or 3 dimensions, and that may not be the case. Your data may not be point sets. So, this may not be so easy to assess. Okay, so probably jumping ahead myself a little bit. So, what is clustering. So, this clustering here is now a noun. So we're going to start with so the input is going to be a set X, and the goal is going to be the output is going to be a partition of X, and this is going to be, what to say, SK. And so the partition of the property that each SI is going to be a subset of X, that SI intersect Sj is going to be equal to the empty set for I not equal to j, and that the union of all I of SI is equal to X. Right? So it's a complete partition of the data. Right? So an example, you have these points are going to be the set X. Then what you may want is to break it into these three groups. So this group is S1, this group is S2, and this group is S3. Okay, so this is some sort of partition of the data. Now, this second one can sometimes be relaxed. So if you don't have this, so if you do not have this constraint where the partitions need to be disjoint, then you say this is a soft clustering. There are variations where a point can be between two different sets. And this can sometimes be useful, especially when certain points, it's not clear what cluster they should be. So, but this really hasn't defined the problem. This is a clustering of the data. But I haven't told you if this clustering is good or not, right? There are lots of ways I can partition the data. I could put, there's a different way where I could say a partition into two sets where the green points here are in one set and the ones not marked green are in another set. That's a partition into two sets, and it's perfectly valid. All the sets are subsets. The partitions are disjoint and the union is the set, but it's not really capturing what we want. So before we get into trying to formalize this a bit more, there are kind of two high-level goals you typically want. So one is the split. So you want SI to be far from Sj for I not equal to j. And so this split is kind of the idea that these clusters are somehow far away from each other. So this is sometimes called the split. There's another notion that's called the width, and you want that x1 and x2 in, or let's say, all x in Si are close. This is far. So that means that all the points in here, all these distances inside of here, all these pairwise distances, you want these to be small, and that's the width. Think of the distance between the clusters to be the split. So you want the width to be small, and you want the split to be large. Okay, so we're starting to get a little bit closer to an answer, but to be clear that, I haven't really defined precisely what's going on here yet. I said I want each cluster Si to be far from every other cluster Sj, but I haven't told you what it means to be far. And the width, I said, I want the points here to be close, but I haven't really told you what it means to be close. This one may be a little bit more clear. because we've talked about distances between points or between objects, you could say all of them are close, maybe this average of them is close. But I haven't really defined here, and these are two criteria, and how do I balance both of them? Well, that's not clear. So, I mean, this is really the clustering problem in a nutshell, and because it's so vague, that's why there's so many different ways of thinking. So we're going to try and give some we're going to go through some ways of thinking about this problem. So any questions so far? All right, so we'll start today with the hierarchical or agglomerative clustering. And again, this is going to be this can be a very simple, a very simple approach, and again with lots of ambiguity, so lots of variations, right? So the hierarchical cluster. Okay. So I'll start by writing down the algorithm in a general form, and then we'll discuss it. Okay, so for all x in x, xi, put in own cluster si. Okay, so for each point, it's initially its own cluster. So you start, if you have n points, you have n clusters to start. Okay, so this is a clustering with n clusters. Every point is its own cluster. Okay. So while two clusters are close enough, then we're going to find the closest two clusters, Si and Sj, and we're going to merge Si union Sj into a single cluster. All right. All right, so that's it. Right. So what we do is you can draw a picture here. All right. So what may happen? I find each of the points are their own cluster. So each of these are their own cluster. I find the closest 2 points, maybe over here. These two are the closest. I make this into a single cluster. Okay? Maybe these 2 points are now the next closest to each other. The clusters are, I make them into a single cluster. And I say, well, these two are pretty close. These 2 clusters are close to each other. I make them into a single cluster. Maybe I stop now. Maybe I say there are no two. There are no 2 clusters which are close enough. Maybe I stop. Maybe I keep going and I say this becomes one cluster and this becomes a cluster. So this is the basic algorithm. Yeah.
How do you decide what is close enough?
Good, right. So that's why there are 2 things I underline here. There are 2 things which are too vague. One is close enough, and the other is how do I define the closest 2 clusters? Okay, I have not defined what either of these mean yet, and that's a very good question. This is how are they close enough? This is the question of you could ask for any clustering algorithm, and So I think I'm gonna handle this one first, but we'll come back to this. And there's no kind of there's no right answer for it. There are different ways we can kind of approach it, though. So we'll discuss this. Okay. Yeah.
So is there a rule in the algorithm you treat all the 2's before you put clump 2's together, or?
Not necessarily, no. I mean, you could define it that way if you want to, but you don't have to. So, yeah, so probably in a lot of data sets, you're going to have these points which are complete outliers that aren't close to anything else, if your data set is large enough. And then you may not want to force that into a pair before you do something else, but in some cases you may want to do that. So I'll talk about some common examples of where this is used, where maybe it'll become clear.
So when you already have a cluster of 2 or more points and you're trying to decide if it's close enough to another, how do you get where is that cluster? Is it the center, or is it one of the points in that cluster?
Yeah, good, right. So let's so let's talk about this. So the distance between Si and Sj. So how do I measure the distance between 2 clusters? Right. So I have 2 point sets. One point set may only have 1 point in it, right? But I have 2 point sets. How do I measure the distance? So what were some suggestions you had?
Closest point in cluster.
So the min of x in Si and y in Sj of distance x x minus y. Right. So this is the closest point in both clusters. So this would be by cluster 1, cluster 2, and the closest point in both of them, that'd be this distance. So this is known as the Hausdorff. This is known as the Hausdorff distance between the 2 sets. So you can define this between continuous sets of points as well. All right, so this is one suggestion. Does anyone have any other suggestions? Yeah.
Could you do not the mean of the points, but within each cluster, the point that's closest to the most other points within that cluster, and use that as kind of the center between clusters?
All right, so let me break this into
Kind of like a midpoint.
a category. So distance between representatives. So Si has so you have some small Si and Si, and you have some small, we'll make these big S's in Sj, and you look at the distance between Si and Sj, because both these are now points, or they're individual. So the individual things you start with X are not necessarily points. They could themselves be sets, but if these are sets, we know how to take this distance, right? So so we look at the distance between these representatives. Now there's a sub-question of how do you choose representatives between the sets, right? So we have this other thing, the choice of representative. And so you, one of the suggestions you said was
It's kind of like the midpoint, but not.
It was the.
I was thinking the mean, but it's more like the point that's closest to the most other points in that cluster.
Most other points, so like a median point.
Most.
Yeah.
So you want to say like a median? Okay, so this is an interesting question. So how do you define the median in 2 dimensions? So the median in 1 dimension, right? So the median of these 7 points is going to be right here, because they're half the points either side, right? But now let's say I gave each of these points some let's see, say I do this. So say some x and y coordinate. Make these points a little bit bigger, sorry. Okay, so I gave x and y coordinates. So in 1D, this one is the median, right? But let's say I looked in the x coordinate, well now this one is the median, but in y coordinate, it's the most extreme point. In the y coordinate, this one's the median. So maybe this one is a pretty good choice, but it's not clear how I get to this one as the median. How do I define it? Median is a really hard thing to define in higher than one dimension. There's a whole kind of there's a whole kind of sub area of statistics that's looking for these robust points in these notion as these higher dimensional medians. There are various things called like the center point. So, which is something that if you look at any half space that goes through this point, at least some fraction of the points are on the other side. And the median, you only look at two half spaces. That's one thing. There's also something called the L1 median, which minimizes the sum of the distances to that point, where the mean minimizes the sum of the squared distances. And the L1 median turns out to be much more robust in some sense than the mean, although it's very hard to compute, and it's not necessarily one of the points. So there are lots of difficulties in how do you define a higher dimensional median. But you could take either of these as your choice representative. So you could say a high D median.
Regarding to the clustering, then the point that's closest to all it's called median. So
The
there's
medioid.
Median.
So what you're trying.
There's also an algorithm called K-median. It's very similar to K-means.
So we'll talk about these assignment-based clusterings, which will work using these representatives. And one version we won't spend much time on because it's actually very hard to compute is based on the L1 or is based on some L1 norm at some point. And that's called the K-medioid, or sometimes the K-median clustering. So I'll mention that either at the end of this lecture or next lecture. Okay, so you can choose some high D median, but you also said something else, which is often a good choice, is just going to be which is just going to be the centroid, and the centroid is actually is just the average of all the points in SI. Yeah, so this is not necessarily one of these points. So I said representative is an element of the set. It does not, the fact that it's element of the set here, that's actually optional, right? So it doesn't need to actually be an element in your set.
How do we decide about the centroid? I mean, SI is not formed and can take any size. So how we can decide a particular centroid?
The centroid, if you have a set already, right, then you can compute the centroid, right? You take and the nice thing about the centroid, unlike this median issue, you can take the average of each coordinate individually, and this gives you the right overall average. So it's a very nice property of the centroid. So it doesn't have this median problem. One thing you can do is take the median of the x coordinate and the y coordinate and use that as a representative, and that's another thing. Though that can be some properties where it's like outside the convex hull, the point set, and there's a lot of strange stuff that goes on here in these higher dimensional medians. All right, so it can be the centroid, it can be the center of the minimum enclosing ball, right? So if you have a point set, then you can define the smallest ball that contains all the points. And then whatever point is the center of this ball, this can be represented. Yeah?
Why not convex, center of convex hull instead of
The center of the convex hull, how do you define that?
probably get the convex hull and then the centroid of the polytope category.
Centroid, so you could integrate over the polytope and take the centroid basic integral, or the centroid of just the points on the boundary.
This is the vertex.
Okay, so there are various ways to define this, but it could be the centroid of the convex hull. So does anyone not know what the convex hull is? Point set. Okay, so the convex hull, the point set, let's say, a point set looks like this. The convex hull is, think of these as like nails in a board, and you put a rubber band around the outside of them, and you draw you could draw a shape like this. So this is known as the convex hull. And so it has, this becomes a convex set, the smallest convex set that contains all the points. So one thing, for instance, that means is that if you took any 2 points in the set, and you drew the straight line between them, this never leaves a convex hull. So it has other nice notions. It contains all the points. And so you may use some sort of centroid of this convex hull, and you can define this various ways, either just of the points in the boundary, or you can integrate it and pick some points. Okay, so there are probably other options here that I haven't listed, but so are there any? So anyone have any other suggestion they want to make? Or?
Is there anything where you do, instead of clustering between points of two sets, you just say this set closest to some predetermined point that I've said, and then sort of split them off by gravitating towards some.
So instead of trying to, so this algorithm is not. So you're saying choose some. So if this is my data set here, I choose 2 points, and then I say which of the points are closest to these, right?
Yeah.
So all the points, and so what that, if you remember from before, we talked about this Mornay diagram. What that does is it basically draws a line where all the points on this side of the line are closer to here, all these are closer to there, and then you assign all these to that. So, so hold on to that thought until Wednesday. That by itself is not going to work that great, but a little help. It'll be a very useful algorithm. Okay, so we can use these representatives, but we don't need to use these representatives. You can also define other sorts of distances between the sets. One of them was this Hausdorff distance. But there could be other distances as well. Right, so yeah?
What about the stability of the sets that are made? For example, if we add in, for example, new points for example, the space that we have, it could cause that these sets can merge to each other and doesn't change all the clustering. Are these?
Yeah, good. So this is a good. Other distance. So we to define a little bit this. So we have to define this a little bit differently, but we do something like some way of measuring the width of a cluster, right? So I have the width defined of a cluster, and I want this to be small. This could be so one way of defining this is the x and y in S, and this would be the sum of all pairwise distances in this set, right? So if I had a point set here, and this was my cluster, I would look at all pairs of points, and I would add up all of these distances, and this could be, this is the width. There are other ways I could define this. I could pick a single representative point, say the centroid, and I could measure the sum of all the distances to the centroid. and this is the width, and then I want to, the distance in between two clusterings is then the distance between Si and Sj may be equal to the width of Si union Sj. So now I define, I don't want the width of any cluster to be too large. So I can consider the union, and I can compute the width and see I don't want that to be too large. Or maybe I subtract off the width of the individual clusters. There are various things you can do.
Instead of a distance matrix, can we do it based on the density of cluster? I mean, we can assign maximum number of points that a cluster can contain.
Yeah, so this is kind of getting into the close enough, right? So this is telling you when to stop. This is not telling you which ones to merge them, right? But that's a good point. So there's a lot that you can do here based on the density, and some of this is based on some notion of width that may be defined like this, and may be defined other ways as well.
Just one information. Can you get width via corsets?
By corsets. Yeah, so you can. There are ways you can do this. My guess, I've not tried using them. My guess is they have really big constants. So there's something we'll mention maybe in a few weeks called corsets, which is a summary of a large data set. And you want a summary of the data set so you can approximate some of these notions without having to look at all the data. And yeah, you can use some of these techniques within clustering. It's kind of a whole subfield that we won't get a chance to talk much about. So there's one other kind of so there are other notions of width. This could be the radius of the minimum enclosing ball. And then let's see, anything else I wanted to mention? Oh yes, so the distance between the furthest pair of points, right? So then you need this min-max notion. So you want to choose, or actually it would just be